Today we're going to look into k-means in a little bit more detail and try to understand how you measure the performance of k-means and what affects the performance of k-means. We're going to use also not the code that I showed you in previous slides that was easier to understand, but we're going to use the more common k-means in sklearn. So there are three main ways to evaluate the quality of a k-means result. Okay, so how do we say if the result is good? So one of them is to count the number of labeling errors. The second is to see the errors in the location of the centroids. And the final one, which we'll see is actually the main one, is to measure the root mean squared error. So let's start with a number of labeling errors. So we have a particular point x, and we can think of the index of the closest centroid to x as the label of x. Okay, so label 1 is if I'm closest to centroid 1. In this case, there is a one-to-one mapping between the true labels and the predicted labels such that most points match, right? So suppose that we have the centroids right on the centers, like where the data was generated, and so we have an exact matching. So this is counting how many mismatches we have. That's basically counting the number of labeling errors, right? So it's not exactly labeling because we don't know whether 1 is a 2 or 2 is a 1, but we can establish a particular matching of the centroids to the centers, and then we can do that. So this is unrealistic because it requires locations of the true centers. Okay, so we need to know where the true centers are. Another one that is also equally unrealistic is that we can match each center with the closest true centroid. So in the good case, the distances between each center and the matching centroid are small. Okay, so much smaller than the distances between centers. And that would be a good thing. Again, it's something that we would like to have, but we can usually not directly measure it. Finally, we have the RMSE curve and the elbow in the RMSE curve. So the RMSE is simply the average of the square distance between the data point and the closest centroid. So the closest centroid that was generated by k-means. So in this case, we don't need to know anything about the true centers. We can just basically use the centroids that we got and measure this distance. And very similar to what we saw in PCA, we're looking for an elbow. So if we look, let's say, at our data, and we match to it one centroid, then two centroids, then three centroids, and then four centroids. If we have like this bump, basically it goes steep into 4 and then it goes very shallow, then we can say with some confidence that the number of centroids is 4. Okay, because 4 explain the data very well, and 5 doesn't improve on that very much. Okay, so we're going to look into k-means and basically see how k-means works under different settings. So to start, let's start with a very easy case. Okay, so we're going to have 4 clusters. We're going to have something called the radius, which is basically defining the distance between the clusters, be a large number, 4. And then for each cluster, we're going to have 100 points. So this case is summarized here. And what we see is that everything works very nicely. So there is a mapping indeed between the centroids and the true clusters. If you look at the classification error, there's exactly one mistake, and this mistake is this point right here, you see, with a little black circle underneath. That's the only mistake. And the error in the location of the clusters is also very small, which we can see visually because if we look at the green triangles, they're right on top of the yellow triangles, they're right on top of the green circles. Okay, so that basically means that the centroids are right on top of the centers and everything is perfect. If we look at the graphs, we see that there is a very clear elbow at 4, which indeed identifies that we have 4 centers. So there are many easy cases like that. You can easily generate them yourself, but we're going to start to look at what makes this problem harder. Okay, so as we saw, this one was very easy, and we had measures that require the ground truth, that we had to know where the centers are, and that worked very nicely too here. So everything was matching. So this is like the classical case in which you'd say that k-means works well. Okay, so suppose that we decrease the radius. This means basically that we make the clusters closer and closer to each other, and the cluster's size stays the same. It's always standard deviation of 1 in each direction. So we're just making them closer and closer. We're starting to get them mixed with each other. So let's see what happens. Okay, so we decrease from 4 to 3. We see that there is some more mistakes, but basically the centers are still exactly at their right place. We decrease to 2, and now we get significantly more mistakes. Okay, so it is important to actually realize that even the correct centers will give us some mistakes in this case, because each point is labeled according to the Gaussian that generated it, not the Gaussian that is closest to it. So if we use the centers and just map each point to the center that is closest, then we still will have actually some mistakes, even if we found the correct centers. Of course, we also didn't find the correct centers, so that adds to the number of mistakes. So let's see what happens if we reduce the number of points. So we started with 100 points. That gave us very good estimates for where the center of the cluster is, because we take the mean of those. It falls right onto the center of into the original center of the cluster. So that's what we had here. But if we reduce the number of points from 100 to, say, 5, this is what happens. Okay, so what you see is that every centroid, the yellow triangle is a little far from the green circle, which is the true center. Okay, so they all have mistakes. However, the clusters themselves, they are far enough from each other that doesn't cause any mistakes to be made in terms of the classification. Okay, so basically these clusters, they're tight enough, the points are close enough to each other that even if you give me a point that is close to the center, I will classify everything correctly. So, so here we see that the effect of having small number of examples is not really devastating. So we saw what happens when we decrease the number of examples in a cluster, and we saw that that wasn't a very big blow. So we will continue in the next video with the same notebook and go and look at some other properties that change when we change the parameters. So I'll see you then.